Okay, very good. Let's start. So I'm Andrea Zonca. I work at San Diego Supercomputer Center, and today, together with my colleague Julian Chastang at UCAR, we're going to present how we've been using Dask to provide users with distributed computing on the cloud, and specifically thinking about Science Gateway. So this talk is mostly for Science Gateway developers, and in the process of preparing this talk, I have created a series of tutorials where you can install all the different components of this setup on Jetstream to be able to have a setup like this configured on your account. So let's first of all start with our platform. So currently we're working on Jetstream 2. We just transitioned. We were using Jetstream 1 before. And the first two tutorials, you see the links here, are about deploying Kubernetes and Jupyter Hub. Okay, so let's take a look at the architecture. So we have our Jetstream. So Jetstream is an OpenStack cloud at Indiana University, and allows you to deploy a distributed system. So let's say, for example, that we have a number of virtual machines. And so first of all, we want to create a distributed system where, for example, we can provide Jupyter notebooks to our users. And so this is useful for Science Gateways, for example, to allow people to use the gateway through the Jupyter notebook, or to post-process the results of the gateway in a already prepared computational environment. And so first of all, we install Kubernetes on those virtual machines so that Kubernetes can handle all of the services that we need to deploy the services, to capture login, to handle networking, to provide the resilience. So if any of the services dies, it can be restarted. And so Kubernetes is coordinating all of this environment, and inside Kubernetes, we can deploy our services. So our first service is Jupyter Hub. So Jupyter Hub is running inside a Docker container, inside a pod in Kubernetes. And when a user comes in, so they connect to Jupyter Hub, they authenticate, and then through the Kubernetes API, Jupyter Hub requests a computational environment to be deployed somewhere in the cluster. And so all the little details are hidden from us because, of course, Kubernetes is handling all the low-level stuff. And so, and then if we have multiple users coming in, they are also going to get their environment. And this is good for interactive computing, but sometimes we want to give our users more computational power. And this is where Dask Gateway comes in. So Dask Gateway is another service that we deploy alongside our Jupyter Hub instance on Kubernetes. So it has two components. So the proxy is just handling all of the necessary networking. And the most important service is the Dask Gateway server that provides APIs so that the Jupyter Notebook users can connect to this server and to the Dask Gateway API and request a Dask cluster to be created for them. And so this, of course, goes through Kubernetes, and we have our scheduler created, just a private scheduler just for that user, and a bunch of workers. So in this example, we just have a couple of workers. And now the Jupyter Notebook user can connect to the Dask scheduler and launch distributed jobs using the very high-level interface of Dask, which from the user perspective is very easy to use, looks a lot like NumPy, but under the hood, you are actually driving computation on a distributed environment. So you have part of an array, for example, is on one worker, the other part on the other worker, but everything is handled automatically by Dask. Okay, and another option to use Dask in our in our environment is actually to provide the capability of using distributed computing to the science gateway itself. And so to provide an example of this, I've created a tutorial where I have a very simple gateway implemented in Flask, is 50 lines of code, that provides an API to launch jobs. So when a user connects to a specific URL, a job is created, and this job is a parallel job on our Dask cluster, and then the outputs are saved on object store. So let's see here. So we have our gateway, which is another service which is running in Kubernetes, and it has its own scheduler, which is dedicated to the gateway, and a few workers, in this case 3. And so when users are connected to the gateway, the job, instead of running inside the gateway, so if you have a computational job, is offloaded to the scheduler, and the scheduler connects to the workers, and then we have this parallel job executed in the workers. And to make the most use of this, of the cloud environment, we are also parallelizing the data output. So all the data that this gateway is producing is going to be directly saved to object store, and so that the workers can, in parallel, all of them connect to object store and create an output file, which is in a specific format, which is optimized for cloud computing, which is ZAR. And ZAR is basically made of chunks, and so each worker can independently write those chunks. And once these outputs are written to object store, then the user can post-process them from Jupyter notebooks, or they are just available for future use. And I've provided a tutorial that goes through all of this and allows you to deploy a very simple prototype system based on this. Now we will switch to a specific case study, and Julian is going to talk about that.
Hello, everybody. Can you hear me okay?
Yeah.
Hello. Okay, great. Okay, hello, everybody. I'll now describe how I employed Andrea's work for a WRF data case study on the Unidata Science Gateway running on Jetstream 1. So back in December, I was approached by a Rutgers University professor to analyze and visualize some weather research and forecast WRF data coming from a climate change simulation. Because of the voluminous nature of the data, it could not be read into memory at once. So the goal was to use Xarray, the Xarray Python library, with a Dask cluster to rapidly analyze and visualize the data in a Jupyter notebook. The Dask cluster was a challenge to build, not on account of Andrea's work, but I had a tremendous amount of trouble coordinating the Conda environments. But once that work was done, everything worked really well. I was able to build a 4-worker, 16-task stream cluster. And by the way, you can find the Docker files associated with this cluster, as well as the Jupyter notebook at that QR code. Next slide, please. Okay, this is simply a screenshot of that notebook, making a wind speed calculation and then plotting those data, and it is employing that Dask cluster that I just described. And it may be hard to discern, but those are wind speeds being plotted above the North American continent. Next slide, please. This is a screenshot of the Dask dashboard in action that demonstrates all the 16 task streams that are running in parallel. I start off the notebook with an embarrassingly parallel small calculation just to demonstrate to myself that the cluster is working as expected. That's what that small, very thin first vertical line is on the left of the task stream. Yeah, exactly where Andreas is pointing. And afterwards, the notebook proceeds with its analysis and visualization. And you can see that all the pistons are firing, all those task streams are going forward. Okay, so I just want to say that I actually just got this working this week on Monday, so I have not many results to present beyond that, I can confirm that running it with one task stream takes about 1,000 seconds for the notebook to run, and running with 16 task streams takes about 300 seconds to run. So we're seeing a benefit in the parallelization, which is great, but obviously I would like to collect a lot more metrics than just that. And that's where the future work will be done. I aim to collect better data and metrics about different chunking and parallelization schemes. And oh yeah, thank you, Andrea. I forgot to mention next slide. Yeah. And just to repeat myself, yeah, I aim to collect better data and metrics about different parallelization and different chunking schemes. And I want to apply it to different data sets with my colleague at Rutgers. And I really look forward to working on Jetstream 2 and the large instances there. And that is what I have at this time.
Very good. Thank you, Andrea and Julian. Are there any questions?
Hi, Andrea. This is Chunhan. I have some question for you. You say like a Kubernetes cluster inside. You are saying like a Dask cluster is running implemented both together, or so I'm just computing that. Like, this means like within Kubernetes cluster, then
Yeah.
Dask like cluster is installed, deployed, right? Something.
Yeah. So basically, the Kubernetes cluster is on top, and the Dask cluster is inside Kubernetes. So basically, each of the Dask service, so the Dask cluster is done by the scheduler and the workers, and they are other pods. Okay, so there is the Dask gateway, which is deployed. Dask gateway is an actual project. So if you if you Google for Dask gateway, you can find their documentation. Okay, so Dask gateway is actually, you see, is deployed on top of Kubernetes, and so it's a service which is running as a pod on Kubernetes, and when someone connects to that pod, can request other pods to be created, and so one pod is running the scheduler, and then you can have any number of pods running the workers. Okay,
I see.
And yeah, and then when the user, and so with Kubernetes you can configure it to have some number of CPUs per worker, some amount of memory per workers, and so you have your distributed cluster of Dask workers that are running as pods inside Kubernetes.
Yeah, pod inside. Okay, I got it. Yeah, thanks.
Yeah,
I think there was just a question, Andrea, in the chat about whether if this runs on OpenStack infrastructure. And the answer is yes, of course.
Yeah. So Jetstream is running is an OpenStack cloud, and so what we do is we install Kubernetes on top of OpenStack. Okay, and Kubernetes itself is connecting to the OpenStack APIs. Okay, for example, we want to provide storage to our users. So when a person connects for the first time with Jupyter Notebook, we want to provide him with some storage, and that's where Kubernetes talks to OpenStack to have an OpenStack volume being created, and then that OpenStack volume is attached to the virtual machine where the user is running. Okay, so there is interconnection between Kubernetes and OpenStack. Okay, and currently we are deploying Kubernetes using KubeSpray. Okay, another option would be to have actually Kubernetes deployed with Magnum, which is the OpenStack service. And I think that's not ready yet for Jetstream 2. And as soon as that's ready, I will want to try that, because the great thing about using Magnum is that we can provide automatic scalability. So having the cluster automatically grow, the Kubernetes cluster automatically grow when we have more demand for resources and shrink when there is less demand. For now, the deployment with KubeSpray is static, so it's always the same number of virtual machines.
Very good. Well, thank you very much, Andrea and Julian. Everyone, this concludes the lightning talk sessions. Thank you very much.